you.
Excellent. Thank you very much, Amanda and Brian, for giving me this opportunity. So what I'll try and do is I'll try and provide some sort of overview, considering the group here. I'm not going to go into the details of the molecular and the deep physiological things that we do. So I'll keep it at a slightly upper level and try to take you through some of the heat stress impacts that we've been studying or looking at specifically in wheat. And most of the work is done after flowering, knowing that our wheat primarily gets affected by heat and drought stress during the grain filling stage in Kansas. And I think it's the same in Oklahoma as well, and other related neighbors. So just to start off here, let me get the pointer. Okay. So we all know that both at the global as well as the regional scale, we are having the increasing temperatures. So if you see here, both the maximum and the minimum temperatures are increasing. But primarily, it is the minimum temperatures that the rate at which they're increasing has become quite rapid over the last 2 decades, I would say. At the region, so why do we actually study high nighttime temperature or nighttime temperature separately is because I pulled this off from a rice study, basically where they looked at the global planting dates and over multiple years, and they were able to show that there are some regions, as you see in Africa or here, both with the day and the nighttime temperatures, their rice is affected or is being vulnerable. But there are some regions, if you look over here in the coastal parts of India or in the Eastern Asia, there are some patches which appear vulnerable to the day temperature, but they disappear. But then there are new patches that appear for nighttime temperatures. So what this whole map shows is there are regions where it could be affected by both day and night temperature, but there are regions where just the day or just the night temperatures could also be impacting the crop. So it's important to take into consideration these changes that's happening both day and night time. So my talk is going to be primarily on the nighttime temperature because that's what we've been focusing in the team over the last 3-4 years, I would say. But also, I would say that we are also looking at daytime temperatures, considering that both of them are important. But I'm not going to talk much about the daytime temperatures. I'll just put one slide over here, which one of my student Blake did while he was with us. We did 2 different experiments in 2016 and 17. We use 7 of the Kansas varieties. Pretty much some of these are locally grown varieties and the popular ones because we wanted to test what is a real reference in terms of the temperature susceptibility or tolerance of some of the genotypes that we are growing right now. And we use these tent systems, as you can see in the pictures over here, where we have the flexibility to move these tents onto the crop at any given point of time or whenever you desire, with what stage you want to stress. So these basically were placed after 100% of flowering, so primarily to target the grain filling stage. And the target temperature that we try to keep is 35 degrees centigrade because we have identified this to be the threshold under field conditions. And when the temperatures go much higher than 35, there is this vent on the top which opens up and then it circulates the air so that the wheat inside doesn't get cooked. So just a final summary in this whole experiments that we did was SY Monument came out to be really tolerant among all the genotypes that we're currently growing in the state, or at least the ones that we tested. And Larry was just behind that. We did do growth chamber studies as well, where you can see that the yield losses pretty much go up to 51% in chambers. And that is quite agreeable because the amount of stress continues at the same level and it's more stressful under the chamber conditions. But you would still see about up to 27% reduction in yield under field conditions. So even under current conditions, with the genotypes that we are growing, we still see quite a lot of an impact with high daytime temperatures that's happening during the grain filling stage. So that means that we still have those opportunity to improve them and for the future weather scenarios that we are looking at. So that was just one single slide for you on the high daytime temperature, just to say that that is also important and we are studying, but I'll use most of my time to take you through with the warm nighttime temperature, which is generally not that well studied or not even considered to such extent as they should be. And I'll reason out why they are very important and that we should consider, especially in case of wheat, which we have done here. So you might ask me why nighttime temperature and why that should be so important, considering that the nighttime temperatures are always much lower than the daytime temperatures, right? So there's a nice study which shows you that it is primarily to do with the planetary boundary layer. And during the night times, this planetary boundary layer becomes very thin. So then any small changes that happens with the temperature has a much more greater impact on what's on the ground, especially like the plants. But the same thing during the daytime temperature, the thickness of that planetary boundary layer is much larger, and therefore it can absorb small changes in the temperature much better than what would happen during the nighttime temperatures. So when I started at K-State was in May 2015, we were not clear on what the real threshold of temperatures were for imposing stress on wheat, right? So the best way to do these threshold studies is using growth chamber studies. So we had 6 different temperatures that we tested. We kept the day temperatures 28 just to be constant, but we only changed the nighttime temperatures. And you can see the profiles over here where we started off with 15 with every 3 degrees centigrade increase leading up to 27 degrees centigrade, because we really wanted to find out what is the temperature where the yield tips off or the quality tips off. So I'm going to cut the story short, and I'm only going to present you something over here, some few highlights. As I said, these are 2 different, we tested about 10 different genotypes, and what you're seeing here are 2 of the contrasting genotypes. SY monument, again, comes out to be really good in terms of high nighttime temperature. So SY monument is one line that seems to be performing better with both day and nighttime temperatures, which is very interesting. And if you look at this is the grain width, and grain width is one of the most important character that is going to be affected with your warming nights. And if you look at the graphs at the bottom, it shows you that SY monument still consistently sort of keeps up even with the temperatures going higher, right? So these temperatures are between 15 to 27, but KS or the M1, which is a contrasting one, seems to fall off with the temperature increasing, right? So we did hear Amanda speak about the protein, and I'm going to give you some pictures just so that it's much more easier to explain this one. And what you're looking at is, again, at the top is a sensitive genotype, and at the bottom is a tolerant one that we looked at. And how we want to look at is look at the four squares in one go. So what I mean to say is, if you're looking at 23 degrees centigrade, anything that you see here in green is protein, anything that you see in red is a lipid, and black is a starch. And this one is basically a combination of all 3 of them. If you look at the sensitive genotype, as the temperature starts to go higher, because your volume of the grain is also going low, but then you have much higher protein concentration as well as a lipid as the starch starts to break down, okay? This is much more clearer when you see the susceptible genotypes, but when you go to the tolerant ones, even at 25 degrees centigrade, they do accumulate quite a significant amounts, but much lower amount of the proteins and the lipids, but still the starch granules, those circular ones that you see, they still seem to be holding up in the SY monument. And this is in the case of the endosperm. And the same thing happens in the germ as well. We did the same thing in germ, looking at different temperatures across these 2 genotypes. And we did do some of this analysis to see that if this changes happens in terms of the proteins and the lipid and the starch in the germ, how is that going to actually impact the next generation or the growth of it if you're like a seed producer? So how is this warming temperatures going to impact your seed quality, right? So this is the summary of that study. If you're interested, the slides will be available. The paper is online as well. Just to summarize what exactly happens to the whole cycle when you have this nighttime temperatures or the warming temperatures, especially during the grain filling stage. So you will have an impact on the negative impact on the chlorophyll and your photosynthesis. So basically your chloroplast starts to degrade, and you start to see rapid senescence. So you start to see your crop becoming brown or golden yellow pretty quickly. So that actually shortens your grain filling duration, right? So when you shorten your grain filling duration, your resources are not really transported, one. Second, some of the resources that you have gained during your photosynthesis or during your vegetative stage is lost for your nighttime respiration because of the damage is caused and for the repair that the plant needs to do, right? So this leads to reduced weight, including the volume, and you have lower grain length as well as grain width. As I said, when your volume goes down, it's very clear that it is the starch that is going to be hit the maximum due to the nighttime temperature. And it's primarily because of respiratory losses where your carbon is being used for maintenance compared to going into the grain and accumulating. So with the gap that is created by the starch, then you see increasing grain protein and the lipid. And these dynamics of changes that happens between the starch, protein, and the lipid then leads to poor germination as well as poorer early seedling vigor. We've done a lot on the gene expression studies that I'm not going to talk to you about. What it primarily shows is the starch and the sucrose synthesis kind of parts are affected negatively, whereas the alpha amylase and the beta amylase, which actually downgrades or degrades the starch in the grain, goes much higher under nighttime temperatures. So that means to say that any starch that is synthesized already in the grain still has a potential to be broken down under nighttime temperatures. Okay. So that basically was a summary of something that we did in the growth chamber conditions. So we wanted to see how things actually pans out in the field conditions, right? So we use the same tents that I showed you for the high daytime temperatures, and I have a very smart student who actually was able to redesign these tents for imposing high nighttime temperatures and the field conditions. And so we had to use a 1,000-liter diesel tank and a generator to impose the heat stress during the nighttime. So the paper is there if you're interested to look at it. And the whole idea was because when you start to go into the field conditions, it's not quite like the chamber. So you really don't know what the threshold temperatures are. So we decided to go with 4 and 6 degrees centigrade above whatever the ambient conditions are. And that's what you see in these pictures. So the blue one is the ambient outside temperature, and the red one is the nighttime temperatures that we were able to impose. And this is the average across the entire grain filling duration. So you're looking at about 4 weeks average that in this slide. And the difference, as you can see, we were able to reach between 3.2 to about close to 4 degrees centigrade. So pretty consistently, we were able to impose this stress. And we didn't have to go up to 6 degrees centigrade, but as I said, that we were really in a trial mode at this point to find what the threshold was. We were able to see that we could see very clear genetic differences, even with 4 degrees centigrade higher compared to what the ambient conditions were. As you can see with these 3 boxes over here, there are some genotypes which are really tolerant to even up to 4 degrees centigrade, but then you see some of those, especially like K26, which is basically one of the breeding lines that we have in the pipeline, to be very sensitive. So we decided that the 4 degrees centigrade was to be the sort of a threshold that we would be testing any of our future field-based studies. So as I said, we also do a lot of crazy things. We basically, not to be confounded by the light, we go out at 3 o'clock or 4 in the morning. We have collected both the leaf and the spikes to do all the molecular analysis. As you can see, there are folks with headlights, and it's quite adventurous with all the liquid nitrogen and stuff. So we do a lot of on the molecular side of things to answer why, the question why, but I won't be talking all on that today. So when you start to look at some of these growth chamber and the field conditions, you might start to wonder how their comparison is across these conditions, right? So as I said, these tents allows us to test these genotypes under the field conditions, and this gives you an indication of what is my losses in even the current conditions that I'm looking at. If 1 degree centigrade rise in high nighttime temperature or your night temperatures, we saw that it would go by about 5%, 5 to 5.6%. As you can see, on an average with all the 12 lines that we tested, we're looking at about 20% reduction in yield, which is like amounts to about 5% per degree centigrade increase. There are some which don't get affected, but then there are some which really get affected. Yeah. So after knowing that there is 5% reduction, we were really like, how do we actually tackle this? So we got a new NSF project where we were able to build the world's first large-scale high nighttime temperature facility here on a farm. So as you can see, we have 6 tents over here. The ones which have the propane tanks are used for the nighttime temperature imposition. We have the generator and the diesel tank, as you can see. And we have a cyber physical system which we have worked with the computer science folks, where the tents actually speak wirelessly between each of them. So the control conditions over here are read by a Raspberry Pi, wirelessly transmitted to this tents over here. As the temperature goes down, then the heating system goes up, and inside there's a tunnel which actually spreads the temperatures very uniformly across the entire tent. And to give you an idea of how big the tents are, you can see that we were able to accommodate our hard red winter wheat panel, diversity panel of 320 lines in each of these tents. So we had good replicates for both controls as well as nighttime temperatures. And if you can see here, again, using the more improved system, we were able to maintain our nighttime temperatures exactly to plus 4 degrees centigrade compared to the outside, which you see the outside one is a blue, and inside the tents is 4 degrees centigrade. So we have a very robust system and a methodology that we have developed over here to test even large mapping populations for high nighttime temperatures. And just to look, so the whole idea was to try and compare how these perform across these scales, right? So generally it's been that controlled environment chambers, it's really hard to replicate under field conditions. So we wanted to try and see how far we can do that. So here in A and D is the chamber conditions, and it is the same 6 temperature conditions that I showed you all during the nighttime. And then the small scale field-based heat tents, as I said, we had the +4 and the +6 degrees centigrade that we tested compared to the ambient conditions of 22. And in the large field-based conditions, it was primarily the +4 degrees centigrade that we tested. So we wanted to see how they actually perform across these scales. And one thing that you want to remember under these conditions is all the 12 genotypes were kept consistent across all these scales. And that was a strategic decision so that we are not confounded by any genetics when we are trying to compare across scales and conditions, all right? So how do they actually perform across these conditions? So the first one is a controlled environment condition. So if you look at 18 and 23 degrees centigrade during the night, you're looking at about 10% reduction, but the same similar sort of temperatures that you see in the large scale field tents, we are about 14%. It's pretty comparable, I would say. And then when you look at 23 versus 25 degrees centigrade, you're looking at 21% in the controlled environments, but similar temperatures that you see in the small scale heat tents, which is between 22 and 25, you're around about 13%. But only when you start to go to very severe conditions, which is like 27 degrees centigrade, and compared to the 23, it's 25% in the growth chambers, but it's much higher in the case of your small scale field-based tents. And the reason is you start to give a lot more water in the controlled environments and you tend to take care of them well. But when you have such higher nighttime temperatures in the field conditions, then it starts to increase your VPD, drags your water out from the soil, and that has a much more impact. So what these studies actually shows us is across all these conditions, if you line these genotypes up, which are the common genotypes that we had, you will see that SY monument consistently performed across all these scales, whether it is a chambers or the small tents or the large tents. And there are genotypes such as M1 and CDAR, which don't seem to perform very well as well. So it's just an indication that some of the work that is done in the chambers is really replicable under the field conditions, and that we could use these scales to test some of the more precise conditions and then be able to make it applicable to the field conditions as well. So that is one trial. And then this actually summarizes all of this work on all the 6 experiments that are out there in high nighttime temperature. The first 3 is from the field conditions, and the bottom 3 is from the growth chamber conditions. And if you see the grain yields, you're looking at about 4 to 6% reduction in every degree centigrade rise across all these studies put together. And then if you look at 3 of the other related traits, which is your grain filling duration, your kernel weight, and your grain number, you're looking at 2 to 4% reduction for every degree centigrade change. So that basically actually summarizes all those work that is out there, both in the chambers as well as in the field conditions. Now you might say, why does this all matter to us, right? Yes, especially under field conditions. So what we did was we actually pulled out 10 years of weather data from the PRISM location, which provides all the weather data. And all these circles that you see is the wheat nursery trials that I got from Alan Fritz, who are a senior breeder. And we pulled all the data out from these locations, and just make sure you keep an eye on the Breton Rouge as well as your Griffin regions. So if you look at this slide, we wanted to compare if it is really relevant what we are doing under current conditions. And in this graph, the orange circles are your Manhattan, and then we put a +4 degrees centigrade, and those are your brown spots that you see. But if you look at Baton Rouge over here, as well as Griffin, you already see that some of the temperatures are higher than the +4 degrees centigrade that we are looking at in Manhattan. So even higher than the stress conditions that we are looking at. So you start to see that some of these wheat that is grown in the southern parts of the US probably are already affected, but we are just not taking notice of them. Last couple of slides from my end, Brian, is it's interesting that we always talk about bread, but we're not talking about beer, right? Which is another thing that we all like, I guess. So this was the study which came out in Nature Plants in 2018, where they studied on the impact of drought and heat stress on Bali. And then they said that there are two different scenarios. It's a low emission scenario and high emission scenario. You can say that it is sort of less worse than the worst case scenario. And the worst case scenario, you would be paying $5 more per every 500 mils of your beer if you're in Ireland, right? So I can't see US. Well, basically, they've not taken US for some reason in their analysis. But what it says is with the lower barley production, your beer costs are going to increase in the future. So my argument is, what about the quality, right? So there are three different traits which the beer production is very keen that they retain it. One is a grain plumpness. So you really want a plumpy grain. So your beer production is really good. But what happens with your warming nighttime temperature, as I showed you, your grains are going to become shriveled. So I think that is a hit to the sort of key trait that the beer production industry will be looking at. And the second one is really they look at the starch, right? Because you really want that starch and your amylases and enzymes acting on it. But when you have your nighttime temperatures go high, when you have more proteins and lipids and lesser starch, that's a second hit to your beer production criteria. And the third one is you want a uniform sprouting for your breeding, for your beer production. But then when you look at some of our varieties, which is a susceptible M1 over here at different nighttime temperatures and different hours of incubation germination, at 15, they do very good, but at all the other nighttime temperature, as you warm them, they never go back to what the controls are, and their sprouting uniformity is also significantly affected. So all these three traits with warming night temperature are not only going to impact the yield, but also the quality, not just bread, but also your beer. Yeah, so that's pretty significant. So some of the take-home messages from my talk are, basically, we're going to start seeing more reduction in the grain yields, and particularly it's a grain width that is going to be affected just because of many of the physiological processes. You start to see reduction in the grain starch, and you'll start to see more proteins and the lipids being accumulated. Probably a functional stay green trait in wheat could be useful to actually protect that carbon loss that might be happening with nighttime temperatures. I pretty much believe that the warming nighttime impacts are not being well qualified at all, quantified, and I think we need to be a bit more serious about that as we go forward into the future. We know quite a lot about bread quality, and we're trying to do something with the warm night temperatures, but as I showed you, the beer quality and quantity will also be affected, which is another area that has been not touched at all, and which is something that we need to look at. So that is my team. Team does very different things, and I'm only presenting a very small part of work that we do. So thank you, Brian. So any questions, I'll be happy to take them.
Any questions for Dr. Jagadish? That was a great presentation. You might check your chat just to make sure nothing was sent in. I don't have anything in my chat box.
Oh, yeah, just Josh, where were temperature readings taken? Above plants, head height in the canopy? Do you ever notice having a good soil moisture made it more difficult to control change in temperature? So these, Josh, so the temperatures are sensors are placed at the canopy level. So that's your first part of the question. So when we look at especially in the case of the field condition, in the first smaller ones, we had limited number of sensors, but when we moved to the bigger scale, we actually spread out, I think, 16 different sensors, all at the canopy level, throughout the tents. And as I said, the Raspberry Pi, all the sensors would average the temperature and send it to the Raspberry Pi. And then that is the average, which is then spoken to the high nighttime temperatures 10. So there was this whole array of sensors that we put it both above the canopy and also 2 meters above from the soil surface as well. So we have different temperatures that we measure, but what we actually consider for our analysis is a canopy temperature. Did you ever notice having good soil moisture made it more difficult to control change in temperature? The soil moisture plays a major role in case of the growth chambers and not so much in case of the heat tents, I would say. In the case of the heat tents, because they're open during the day, you lose a lot of that moisture because the conditions are really hot. And so we really have to water them, and we have the watering system also. So we made sure that we are not impacted by a lot of dryness or the drought stress as well, and that we are capturing most of the nighttime temperature impacts. So that's the answer. And then we have another question. Does the increase in nighttime temperature have a similar effect on corn and soybeans? Great question. Regarding soybeans, I'm not sure, but we have a new USDA NIFA grant that we are using a small tens, but that's with high daytime temperatures. With the nighttime temperatures, as I can see, the cereals which have the higher amount of starch is the ones which are going to be more severely affected. Especially, I've worked a lot on rice and wheat, and I know that these have a lot of starch in them. Corn, since we have done 2 years of wheat, we are doing corn right now. So we are looking at multiple varieties from 4 different companies, and I'm trying to make sure that they allow us to publish that. So we are going to test that corn as well, Tom. And so hopefully after this year, I'll be able to tell you how much corn is being affected in terms of nighttime temperature. But in case of soybeans, I would say it would be lesser because it's more protein. There might be slightly more protein, and you would lose a little bit of starch, but not to the same extent that you would see in rice, wheat, and corn, if that answers your question.